we are going to look at e.m.f and internal resistance. I'm just going to go through what these terms mean and then we'll see how they all link up together. So e.m.f is also called electromotive force. You need to make sure you know both of those terms because sometimes it's written as one and sometimes it's written as the other in questions. And the e.m.f is the maximum voltage that a source could provide to a circuit. The reality is that what's actually in the circuit is always slightly less than that, and we're going to come on to why that is. So it's the maximum voltage a source could provide. So it's measured in volts. Joules per coulomb is also acceptable. Internal resistance of a cell. So when the electrons are going through a cell, there's going to be some resistance in that cell. So each cell or power supply has got a small inbuilt resistance, and that's called internal resistance. We write that as a small r so that just to identify it as it's being separate to the resistance in the rest of the circuit. Lost volts is another term that we need to know about. So lost volts is basically the lost voltage that occurs because of the fact that we've got this little bit of resistance in our cell. So the resistance in the cell means that the e.m.f that we could provide to the circuit is not the same as what actually gets provided to the circuit. The difference between the two is the lost volts. So lost volts is worked out by doing current times the internal resistance. Terminal potential difference, which up to now we've just called potential difference or voltage, is the voltage that the circuit actually gets. So this is the voltage in a circuit when you put a voltmeter across a component within that circuit and what you read. So the terminal potential difference. So as I said, that's slightly less than the e.m.f, and the difference between the two would be the lost volts. To work out the potential difference in a circuit, you just do current times resistance. Load resistance is just the resistance in a circuit. So just V equals IR. To work out what the e.m.f of a cell is, we can either connect a voltmeter directly across a power supply or a cell, or we can connect it into a circuit but just have the switch open to start with. So this switch is open, which means this voltmeter is essentially just connected from one side of the cell to the other. Mr. Mitchell's done a video that goes through this as well, so you'll see he has done the experiment in class. You notice that the cell's drawn slightly different to normal. So when we're doing questions that are related to e.m.f, the cell will be drawn with a little resistor beside it and a dotted line round it. There's not an actual resistor in the cell, but the cell has got some resistance, so we just draw the little resistor in there to basically to show that we're acknowledging that there is some resistance within the cell which is going to affect the voltage available. So this is what I've done here. I've connected a voltmeter across a 1.5 volt AAA battery, and you can see that I'm actually getting a voltage of I've connected a voltmeter, sorry, and I'm getting a voltage of 1.6 volts, even though it should only be 1.5. So that's basically a little bit extra that's in the cell to allow for the fact that we lose a bit because of these lost volts. So the lost volts in this case would be 0.1 volts. To measure the TPD, or what voltage we actually have available to us, we just put something into the circuit and then measure the voltage across that component, often a variable resistor. So this voltmeter would then record the TPD, and then we would then know the difference between that and the e.m.f, and that would be the lost volts. So the lost volts is worked out by doing current times the resistance in the cell. The TPD is worked out doing the current times the resistance in the rest of the circuit. Put those together, gives us the e.m.f, and that simplifies down to look like that. We can also connect a wire straight across a cell. If we do that, then, so a wire that's got pretty much zero resistance, we connect that straight across. That's similar to what we did with the voltmeter, and then the cell has been short circuited. Now at that point we've got an external, big R is 0, I is the short circuit current, and that is potentially quite high and is dangerous because basically all electrical energy is just getting converted straight to heat into the wire because there's not anything else there. The short circuit current is the maximum current that could be supplied by a source. So you're still V equals IR, but using your maximum voltage, your maximum current, and the internal resistance of your source. So to find out what the EMF and the internal resistance of a power supply is, what you can do is connect up a circuit like this. So the voltmeter is connected across the power supply or the cell. We've got an ammeter in here, and then we've got a variable resistor. So the variable resistor changes. As the resistance changes, that's going to affect the current, and it's going to affect the voltage. This is the TPD it would be measuring because it's a proper circuit. We can then look at those two and compare those numbers. So take various numbers, and you then plot a graph of the TPD on the y-axis and current on the x-axis. Gives you a nice straight line, and looking at that straight line, we can then think about what you know from maths, that the equation of a line is y equals mx plus c. So y is V, which is the TPD. That's what we're reading on our voltmeter. M is our gradient. I'll come back to that in a second. X is obviously our x-axis, which is the current. And C is the point where it intercepts the y-axis, and we'll come back to that. So when I equals 0, that's the point when that's basically where we've got our maximum voltage. So that's the point where our line is crossing the y-axis. Okay, so at that point we can rearrange, well, change the C to an E. So E would be EMF, is what it should really say. If we then compare that to our V plus IR, that basically tells us that the gradient of the line is the same as our internal resistance. So you can work out the internal resistance from the gradient of the line when you've taken this selection of numbers. Okay, that makes more sense now. Should have put that up to start with. So where it crosses the y-axis, that's our EMF, because that's the point where the current is 0. And our maximum current that we can get, so our short circuit current, is obviously where it then hits the x-axis, so this point down here. The gradient, now because it's downhill, it's minus, so the gradient is the internal resistance. We basically just forget about the negative, it doesn't matter. So here's an example. So current setup, similar to the one we've just looked at. We've got just 3 points have been taken, so they've taken 3 readings. So we've got 2 amps, 16 volts, 4 amps, 12 volts, 6 amps, 8 volts. So use the graph to find the EMF and the internal resistance of the cell. So what you have to do with a graph like this is you extend it back. So you would use a ruler and then extend it back until it crosses. So just going as straight as I can with the mouse. It looks like it's going to be maybe 22, somewhere around about 21, 22 volts. We could, it's not actually asking us to, but we could also go this way and down to work out the short circuit current. Obviously we'd have to extend this as well. The short circuit current looks like it must be at about 9 amps, I think. So EMF is, so they've got it as 20. I thought it was slightly higher than that. So they've set it as 20 volts, so it's where it crosses up here. And then working out the gradient of the line gives us an internal resistance of 2 ohms. So that's just using y equals mx plus c to work out the gradient of the line. So we've got another one here. A cell with an e.m.f of 1.5 volts, internal resistance is 0.75 ohms, is connected up. So saying calculate the value of the reading on the voltmeter, and what's the value of the lost volts. So the reading on the voltmeter, we say that V is I times big R plus little r. So the 1.5 is the EMF. The reading for the current is, that's what we're trying. So we don't know what that is. Add the two resistances up, gives us, then rearrange that, gives us a current of 0.4 amps. We can then do V equals IR to work out. So I is now 0.4. Resistance is just the resistance here. So we're just the external resistance. 0.4 times 3 gives us a TPD of, that should be 1.2 volts. That should not be an ohm sign. That should be a volt sign. The lost volts. So there's two different ways to work out the lost volts. We can just do the difference between the two. So we already know that the EMF is 1.5. So you can just do 1.5 take away 1.2, which would give you 0.3 volts. Or you can say that lost volts is equal to I times little r. So the I is 0.4, little r is 0.75, and that gives us the 0.3 volts. Okay, so it's just two different ways to work out the same thing, and that should be a voltage sign. I'll correct that on the one that I'll upload. Oh, that's just what I've just done. Okay, hopefully that makes sense. I'll do a worked example with a graph question as well, I think, for you.